Hi kids, this is Miss Nichols, and this video is on sound, hopefully something that is interesting and relevant to your lives. The essential question for this video is, what is sound, and how do the wave variables that we've learned about impact the sounds that we hear? So let's start with what sound is. Well, sound is a series of longitudinal pressure pulses, or waves, and this is why we're talking about it in this unit. Sound is a wave that can go through any mechanical medium. So it can go through air, obviously, that's often what we hear sound through, but it can also go through water, right? You've heard whales talking through water, and it could go through rock even. Glass is a rock, and if you yell through your window, it can get through there. So sound can go through almost any medium, although it frequently is traveling through air. The human ear is a magical organ, which we'll talk about in a little bit, that has evolved to detect some sounds. Not all sounds can we hear. We can only hear a certain specific range of those sounds, but we use that ear to detect these waves and translate them into useful information. Our brain, of course, is the other hearing organ. We talk about that in science sometimes, because it's our brain that categorizes and interprets these sounds. In other words, it gives the sound meaning. This is kind of a representative image of what sound is like from your speaker. So your speaker has a cone. If you've ever touched the speaker of your phone or touched a speaker in your house, you can feel that cone vibrating, and it's creating these pressure pulses in the air, which are going to get into your ear. So that's the sound. It's the pressure as it moves through the air. So all waves must have a wave source. For sound, almost anything can be a sound wave source. All it has to do is vibrate the air. This is a little video of some crickets making sounds. Crickets actually make sounds by rubbing their legs against each other, and that makes the quintessential cricket chirp. So as they rub against their body, they vibrate against each other, and that's what makes the sound. Maybe you've heard the old conundrum of, if a tree falls in the forest, does anyone hear it? Or does it make a sound, I guess is the question. And the answer is yes, because sound is defined as a vibration in a medium. And obviously this tree is going to be vibrating the air, whether or not someone is there to hear it. Humans, you can use lots of things to make sounds, right? We could use our hands or our elbows, we can clap, we can do all sorts of stuff. But often, the most sounds that we make come from our vocal cords. So vocal cords are these things in your throat. Sorry for the kind of graphic biology image. Some of you guys will be interested to see what you see if you look down your throat. You have these two flaps, and you push air out of those flaps, and at the same time the flaps vibrate, and vibrating that air is what makes sounds come out of our mouths. Fun fact for you all, the giraffe is one of the only animals, maybe even the only animal that we know of that makes, no, there's got to be other animals. But anyway, giraffes make no sounds, so they're totally silent. They communicate through other ways. So we've got all these sound waves in the air, but how does our ear actually hear these things? Well, the ear is kind of complicated. There's a bunch of parts on the ear. The first part that we talk about is called the pinna, and the pinna is the outside of the ear. It's the big flappy thing hanging off the side of your face. The point of that pinna is to act like a funnel. It basically collects sound and channels it to the little hole that goes inside your ear. Inside that hole, we've got all sorts of ookie gookie earwax, etc. I should be drawing this with yellow maybe. And earwax, believe it or not, has an important function. The function of earwax is to act like a dust trap, because in the air, there's also lots of dust and grime and junk, and we don't want that dust getting into these sensitive organs deep inside our ear. So the ear wax does us a favor and captures that dust, and then earwax kind of falls out of your ear eventually and carries the dust with it. If you go past the earwax, there's an organ that probably many of you guys have heard of, known as the eardrum, and that's this guy right here. It's called an eardrum because it looks like the surface of a drum. Its fancy name is the tympanic membrane, but it's the eardrum, and it's basically a little flap of skin that goes entirely across your ear, and it acts just like a drum would act when you hit it with a hammer, when the air hits it with the sound waves, and it starts vibrating back and forth just like a drum. Behind that eardrum, there are 3 tiny little bones. These are actually the tiniest bones in your body, right there, 1, 2, and 3. This last one's called the stirrup. Looks just like a stirrup from a saddle if you've ever done any riding. But the point of those bones is they're attached to the eardrum, and when the eardrum vibrates, the bones start vibrating too. The last little bone, that last little stirrup, is touching this big snail-shaped, disgusting-looking organ in your head called the cochlea. And the cochlea I like to describe as a big water balloon full of goo of some kind. And so when that stirrup bone hits that cochlea and makes it jiggle, it's like shaking a water balloon or shaking a plate of Jell-O. That whole cochlea is going to shake. On the next slide, I'll show you what's inside the cochlea, which is kind of interesting too. But the cochlea is attached to one last thing, which is these guys right here, and these are nerves which go to your brain. I realize I'm drawing your brain very small, but you guys are only freshmen in high school, so your brains are pretty small so far, but they'll grow, don't worry, they'll get bigger. So these nerves that are connecting to the cochlea take the information of that sound and send it to your brain, where your brain figures out what the sound means. So what wave variables can your ear actually detect or notice through all of these complicated organs and complex mechanisms inside your brain? Well, the key is inside that cochlea. Inside that cochlea, there's actually a bunch of ear hairs. Look at these things. They're growing inside your ear. They're gross. And some of them are really long, and some of them, as you spiral in towards the inside of this little snail, they get smaller and smaller and smaller and smaller. So those ear hairs are the key to everything as far as what our brain can detect. Our brain can detect the frequency of a wave, because different frequencies make different ear hairs jiggle. And I'll do a demonstration for you in class to show you how this works. But in general, the longer the ear hair, the lower frequency is going to make it jiggle. And if you have a little tiny one, you need a high frequency to kind of make it jiggle. You can do this experiment at home with like a ruler and a meter stick, and you can picture trying to make them vibrate back and forth. The ruler is going to have to vibrate really fast to make it go, and the meter stick you would be going slowly because it's much longer. So same idea. So those ear hairs can detect different frequencies. They can tell your brain what the frequency of the sound that you're hearing is. They can also detect the amplitude of the wave by basically how far each ear hair is jiggling. So how much energy is in that wave will determine how far those ear hairs jiggle. So sound frequency is something that we interpret as humans as the pitch, or sort of high or low of the sound. So low frequency is a low pitch. Low frequency is a low pitch. The wave source is not vibrating very many times every second. If you make a low pitch sound with your voice, and you put your fingers on your voice box here near your vocal cords, you can feel the vibrations, and they're relatively slow. High frequency sounds like a high pitch, and that means the wave source has to be vibrating many more times every second. If you put your hand here again and then slowly get higher, so you'll feel the vibrations speed up and up and up, and eventually they're going so fast you can't even feel them as a vibration anymore when we get to the really high-pitched sounds, because they're vibrating faster than your finger nerves can detect. The typical hearing range for humans is between 20 and 20,000 hertz. 20 hertz is 20 vibrations a second, so those low-pitched noise, your vocal cords are still vibrating 20 times in a single second. And the high-pitched noise is the highest pitch you can hear. That horrible sound that makes you cringe is 20,000 vibrations every second, which is kind of amazing that we have an organ that can detect that sensitive of a vibration. Sound amplitude is, of course, just like amplitude is for any wave. It's a reflection of the amount of energy in the wave. And in general, more amplitude means that the medium is being displaced more. The air has stronger or tighter pressure pulses. And so when I'm making these sounds, I put more energy into it that squishes the air together into these tighter packets. Our human brain interprets this amplitude as the volume of the noise. It's the amount of energy that's in the noise. So a very quiet sound is a very low amplitude, and a loud sound is a high amplitude. High amplitude sounds can be really dangerous for your ears. They can actually break that eardrum if you get a loud enough sound that hits it. That thing that Coast Guard employee is holding right there is known as an LRAD, and it was actually in the news recently. It stands for Long Range Acoustic Device. The military developed a weaponized sound, right? So this is a sound that is so loud that it can burst your eardrums, which it turns out is incredibly painful. They thought the Coast Guard used it for a while against pirates, believe it or not, in the ocean, but then the pirates got smart enough to put on earphones. And so usually it is used in crowd control situations. And of course, when we have riots and things throughout the country, sometimes the police departments will get them out. And there's been a lot of debate about whether that is humane or not. I'm not going to come down on one side or another of this in the political atmosphere of today, but it is typically non-lethal, but incredibly painful and life-altering. Of course, if you get your eardrum shattered too much, then you lose the ability to hear. So anyway, sound amplitude can be turned into a weapon if you make it big enough. What about the speed of sound? Well, the speed of sound is a wave, and so the speed of sound depends on a medium. It's kind of a tricky question. I think most people think that sound has a speed, and it does have a speed in air. So there's a typical speed of sound in air, but sound goes at a different speed in glass or water or rock or jello. You can't change the speed of the sound based on the frequency or the amplitude. The only way to change the speed of the sound is by changing the medium. Think about it. If you were listening to a concert and different frequencies had different velocities, then like the high-pitched noises would get to your ear before the low-pitched noises, and that would sound like a total mess, right? All the sound arrives together. It doesn't matter whether it's a high pitch or a low pitch. It gets to your ear at the same time. High volume, low volume. You never you can't whisper and then shout and have the shout pass the whisper, right? The whisper always gets there first. So the sound velocity depends entirely on the medium. Sound, interestingly, is fastest when it moves through solids. I think most people tend to picture solid objects like glass as slower velocities, but for sound, it's actually fastest because the bonds between the molecules are rigid. So solid objects are made up of crystals, and the atoms in them are holding really tight. It's like a whole bunch of people packed up next to each other in a room, and I would do this demo if we were in class together. I'd pile you guys up next to each other in a room, and then I'd shove one person on one end, and everyone would be together, and it's basically like a whole bunch of dominoes. That wave goes really quickly when you're all touching each other. Liquids, at the speed of sound in a diamond, which is the fastest medium, is 12,000 meters every second. So this is a meter, right? 12,000 of those in 1 second when we're talking about going through diamond. Liquids are sort of medium speed. Liquids have floppy bonds, so this would be like holding hands with your neighbor, and I push a wave on one side and you're holding hands, and it sort of eventually flows through the chain of people, slower than the solids. And then it's actually slowest when it moves through gases because the molecules aren't touching each other. So when I want to send a wave through gas, I have to hit this molecule on one side, and it has to move through space and then hit this molecule and then move through space and hit the next one. So it's actually slowest through gas because they're not actually bonded with each other, but it's still pretty darn fast. Sound moves at about 350 or 340 meters every second. This is kind of a model of showing how a wave would propagate faster through the solid than the liquid than the gas. Your brain can't tell how long it took sound to get to it because I don't know when the sound left. All I know is what it sounds like when it hits your ear. So we can't tell what medium we're in. We can't detect velocity, right? Your eardrum can only hear amplitude and it can hear frequency. It cannot detect velocity. However, one kind of cool thing that you can detect is the difference in time that it takes a sound to get to one ear than the other. And this is the reason why we have two ears, because it takes, the sound is going to arrive, if the sound is coming over here from my left, it's going to hit my left ear before it hits my right ear. And my brain can actually calculate the difference in time it took to get to one ear to the other, and it can work its way backwards to figure out, generally speaking, the location of the object that made the sound. Our eyes do the same process, actually much more precisely than our ears do, so we're not going to talk about it a lot here, but it's kind of a cool idea that you can hear a sound and know where it's coming from based on the difference in time for your two ears. Music industry and video games and movies use this to make it sound like a sound is coming from a certain part of the screen. If you've got a headphone on, for example, it sends the sound at a little bit different speed to the left phone than the right phone, and that your brain interprets that as coming from a certain side of your head, which is kind of neat. The last wave variable is the wavelength, which is actually kind of the least interesting one for sound. Audible wavelengths in air are typically about this big, centimeters to meters. So the sound waves that you're hearing right now coming out of this video are about this far apart, which is, I think, bigger than most people predict. And you can calculate the wavelength based on the velocity, which depends on the medium, and the frequency, which depends on the wave source. Same equation, wave equation, holds. Linear relationship with velocity and an inverse relationship with frequency. Note that the same wave is going to have different wavelengths and different medium, and your ear can't actually tell the difference. So if I listen to a sound in air and then go underwater and listen to it, it sounds the same to me because we hear the same frequency regardless. The wavelength of that wave would be different, but my ear can't really detect that. Okay, well, hopefully you guys learned a few new things about sound today, and we'll do lots of demos and fun activities with this in class. The essential question, please take a few minutes and write down your interpretation of the answer to this. What is sound, and how do the wave variables impact the sounds that we hear? And here's a little Calvin and Hobbes comic to run out the end of the video. Thanks for watching.